All right, so welcome to the second to last week of class. Yes, you heard me right. The second to last week of class we have this week. Next week we're off for Thanksgiving, and then we have one more week, and then a final exam. So 2 more weeks of class, and we'll be out of here. And today's plan, I want to remind you a little bit about what we did on Friday, which was the applied max-min stuff, the optimization. So we'll do another example of that. And then we'll turn our attention to this thing called Logitel's rule, which is going to help us when we want to evaluate limits. We'll actually relate this back to some of the stuff we did way back in September. So that's the plan for today. But before we do that, as always, let me open it up to questions about homework or anything else we've been doing in the class. All right, hearing none and seeing none, then I guess I'm going to go with that things are going okay that way. So give me 1 second and I'll switch to the whiteboard. All right, so last time we talked about optimization, and optimization is really what it sounds like, trying to get best possible case scenario, trying to get the most of something or the least of something. And we saw how we could use calculus to do that. We had to create an equation that involved just one variable. Then we could differentiate it, look for critical points, test the critical points, and it would give us the extrema, right? And so then we would optimize our problem. So I want to refresh your memory. I'm actually going to do two. We'll do kind of a quicker one, and then I'm going to show you one that's a pretty common kind of problem that we'll see a lot. So here's a little kind of review type question. All right, so what we've got is, let's say we're making a poster. Okay, so we're going to be making a poster. That needs to have borders. Okay, so this frame or this poster, we're going to need to have some sort of a border around it so that we can frame it, whatnot. Okay, so obviously we can't use the entirety of it. It is going to be rectangular. But here's what we need. We need 1 inch borders on the top and bottom and on the sides. All right, so just think about like my whiteboard here. If this was our poster, we need to make sure that there's an inch strip on all 4 sides. All right. So we need those guys. And then what we need is 120 square inches of area inside the borders. So the actual usable area, needs to be 120 square inches. So my question here then is, what dimensions will optimize total area of the poster? Okay, so I just want to figure out, once we get our usable space, what's going to optimize the total area of the poster. All right, so kind of typical optimization problem. So remember what we have to do. We need to figure out what we're optimizing, get an equation for it, make sure that equation is only in one variable, and then do the calculus. So let's draw a picture. So we've got a rectangular poster. We need to have 1-inch borders so that we can frame it properly. So it looks a little bit like that. We know that we need 120 square inches of area on the inside. So that little bit is 120 square inches. And we're trying to minimize total area. Right? I just said minimize here. I said optimize. We'll see that it is a minimum. But we're trying to optimize the area of that thing. All right, so let's think about what we know. We know that we have 120 square inches on the inside. And so since that's a rectangle, we know that it's base times height. So how about I call these X and Y. Okay, so X and Y are going to be the dimensions of the usable area. And so what we know from that is that X times Y equals 120. Now, that is not what we're trying to optimize, but that's our constraint. Hopefully you remember that word constraint. That's the that's a restriction on our dimensions. So we are restricted to X times Y equals 120. Now, what we're trying to actually optimize is the area of the poster itself. So that means we need to know these lengths, because the area is going to be those two multiplied together. All right, well, how are we going to find those lengths? Can anybody see a way to describe, let's say, this width, this red big width, in terms of X and Y? Throw it in the chat box, yell it out. All right, cool, thanks, Ayers. Ayers just put in the chat box, X plus 2. Right? Oh, and then he's anticipating my next question, which is the other one, which is Y plus 2. So this is going to be X plus 2, and this one's going to be Y plus 2. Okay, so some of you might be looking at going, wait a minute, why the plus 2? Well, that was from the borders. Remember the borders, we wanted an inch, 1-inch border for each of these. So if you think about the width, it's going to be the width of the usable area plus 1 inch on either side. And there's your X plus 2. And similarly, Y plus 2, we're going to have that Y height plus 1 more inch on either side. So that means the total area is going to be X plus 2 times Y plus 2. So if you go back and you look at your notes, I kind of gave you a 3-point plan for these. Right? I said first step was find the equation that we're trying to optimize. So that's that right there. We just did step number 1. Now we're ready for step number 2, which is get that only in terms of X and Y. And this is where our constraint's going to come in. That constraint up there, that X times Y equals 120, we can actually solve that for one of the letters. How about just for Y? It equals 120 over X. And if I substitute that in, this thing turns into a function of only x, which is what I want. So now we're going to be able to use calculus on this and optimize. But before we do that, let's FOIL this, because it'll be a little bit easier to differentiate instead of using the product rule. So if you multiply everything out, you're going to get 120 plus 2x plus 240 over x plus 4. So basically, this is just saying, if you tell me how wide the printed area is, I can now calculate the area. I just plug that x in. All right, so there was step number 2. Get it only in terms of x. And we've done the hard part, because now this is going to be easy. This is just good old differentiation and optimization. So let's get a prime. So the 120 goes away. The 2x gives me a 2. The 240 over x gives me a minus 240 over x squared. And the 4 gives me 0. All right, so now we're going to look at where is this thing 0 and where is this undefined. We're going to get critical points. All right, so if we look at where this is equal to 0, we're going to get 2 minus 240 over x squared equals 0, which is x squared equals 120, which is x equals plus or minus the square root of 120. I'm just going to leave it there, square root of 120. It's good enough. It's close to 11. It's very close to 11, just a little bit smaller, but that's the exact value. Okay, so there are 2 critical points. We also want to look at where a prime is undefined. And that's going to happen when x is equal to 0, right? Because if we plug in 0, we're dividing by 0. All right, so far so good. All right, well, now let's talk about those different critical points. So first of all, we're going to throw away x equals 0, because x equals 0 is dumb in this case. And in fact, x equals 0 doesn't work. If x equals 0, that means that the usable width is 0, which means we don't have a poster to use. Okay, so we're going to rule that one out. Okay, so the plus or minus square root of 120, I'm going to eliminate the negative also because of reality. Think about what that would mean. That would mean that the width of our poster is negative. That doesn't even make sense. So I'm going to go ahead and eliminate that one as well. Real quick, I just noticed, Alia, you have your hand raised icon up. Do you have a question, or is that just accidental? Okay. So we're going to eliminate the negative because that doesn't make sense. So the only of these critical points that would make sense anyway would be the square root of 120. Well, let's just make sure that that actually is the correct, that actually does optimize it. And in fact, let's see that it is a smallest. If we do a double prime, so you take the derivative again, you're going to get 480 over x cubed. And just notice that if x is positive, which we are in this case, then a double prime is positive, which means it's concave up. If it's concave up, that means this point gives us a minimum. All right, so what we know then is that in order to optimize the total area of the poster, we're going to get a minimum when x is the square root of 120. So just around 11 inches. So the entire poster, we'd need to add 2 inches on to its width. So it'd be the square root of 120 plus 2. And then we could plug that in to figure out what y would need to be. Turns out it's the same number. Again, to minimize this thing, it would have to be a square. All right, so hopefully this is kind of a good little refresher for the process, what we did last time. This one's actually very similar to the building the fence around the corral problem that we did on Friday, which is kind of why I wanted to start with this one before we go to a very different looking question that still requires us to do the same thing. It's just going to be a different formula that we get. All right, so before we move to another example, we good with that one? Any questions that I can answer? No. All right. Okay, so let me give you this one. This next problem, there are a bunch of problems that are like this. They're all very similar. And I call this the lifeguard problem, and you'll see exactly why. Okay, so suppose what we have is a beach. And so here's a beach. And we've got a lifeguard who's stationed up on a little lifeguard tower at the beach. Now, this lifeguard is being very diligent. She's paying attention to everything and sees off in the water somebody struggling. Okay, so there's somebody down here, right, who's in the water and starting to have a problem. Okay, so lifeguard sees this and was like, oh man, I gotta start going. Now, here's the deal. Like every lifeguard, she runs over the beach at a different speed than she swims, right? She's a really good swimmer, but she can't swim as fast as she can run. And so the question is, where should she run to on the shore before she starts swimming? Right? She's got some options. She could run like straight to the water and then swim out to the person. She could run out on the beach until she's equal to where the person is and then run out and swim. Or she could go somewhere in the middle, right? I mean, she could even do a straight line. Like there are a bunch of different options, but the question is, where on the beach, where at the waterfront, should she run to and then start swimming? Okay, so what is she trying to optimize here? Like if you think about it, what is she trying to either maximize or minimize? Yeah, let's go to time. It's all about time, right? The clock is ticking. The longer it takes her to get to this person who's out struggling in the water, the more likely that person's going to drown, right? So she's trying to minimize time. So here's going to be our goal. We want to minimize the time. I don't know what minimize is, but minimize the time. All right, so what information do you guys need to figure out how to minimize the time? Can you think of some things that you need to know? Okay, so Eris just put in distance. For sure, we need to know how far away things are, right? Because time definitely involves distance. And then Mariola, she just put it in the chat box. You also need to know the speeds. How fast does she run? What's her swimming speed, right? So think about it. We just heard we need distance and we need Speed. Hey, isn't that just good old dirt? Distance equals rate times time, right? This is a distance equals rate times time problem, good old dirt problem that you've seen before. So if we're trying to minimize time, here's basically what we're going to need, right? The time, we'll write here total time equals the time running plus the time swimming. To get those, we need distance and rate, right? So this is going to be the speed divided by distance. So I'm going to put here speed run divided by distance run plus speed swim divided by distance swim. Except I've got those backwards. It's distance over speed. Sorry about that. All right, so we need the distances and the speeds. So let me give you some information. In terms of swimming, she can swim at a speed of 5 feet per second. And she can run at a speed of 15 feet per second. So she's 3 times as fast running as she is swimming. All right, now in terms of some distances, she is currently 50 feet away from the shore. The person who's struggling out here is 30 feet from the shore. Let me just erase some of this stuff so we can see a little bit clearer. And then it's actually 200 feet from where she is to where this person is floundering. Okay, so I just gave you distances and speeds. So let's see if we can set this thing up. So in terms of the speeds, let's just go ahead and put those in. Those are nice and fast. So her running speed is 15 feet per second. Her swimming speed is 5 feet per second. All right, so now we need to get the distances that she swims and runs. All right, well, that kind of depends on where she enters the water, right? Because like if she did the just run straight up to the beach and then swim, she runs 50 feet and she swims whatever that diagonal would be. Or if she ran straight to the edge here and then swam directly up, well, her swimming distance is 30 feet and her running distance is whatever that diagonal is. But she also could stop anywhere in between and jump in. So what I'm going to do is I'm just going to mark a random point and say that's the route she's going to take. So in terms of those distances that she's running and swimming, It's those two lengths, these two green lengths, that I need to calculate. All right, so what do you think? How are we going to figure out those distances? What are we going to use?
Pythagorean Theorem.
I think the Pythagorean theorem sounds lovely. Right, we got ourselves some right triangles. So where is she entering? I don't know. I'm just going to say that this is a distance of x. It's variable. It's going to be something between 0 and 200. I mean, I guess it could be more than 200, but that's definitely not going to minimize time, right? If she runs past where the swimmer or the person swimming is, and then she has to swim back to them, right? It could also be less than 0, but that's silly too. She's running away and then swimming further. So we're just going to go with that, call that x. So this distance right here from the Pythagorean theorem is going to be the square root of 50 squared plus x squared. So if you tell me how far down the beach she's going to hit where she's going to hit the water, that distance, I plug that in here. That gives me how far she runs, which then when I divide by 15 gives me the amount of time she's running. So let me go ahead and put that in here. This is 2500 plus x squared. So that fraction right there, that's how much time she's actually running. That's the number of seconds that she's running. All right. Well, now let's look at this other distance. It's going to be another square root. I don't think you can see that because of the glare. So this is going to be another square root. For the Pythagorean theorem, it's going to be 30 squared plus, well, I need to know this distance. Let's call it y for right now. So y is the remaining distance down the beach. So in terms of that Pythagorean theorem, this is going to be the square root of y squared plus 900. All right, so we've done the bulk of the work. We have the thing we're trying to minimize. We're trying to minimize that time. So there was step number 1. So you notice that this came from a very different thing, right? We didn't use areas or anything. We used Pythagorean theorem. We used the dirt formula. But we used things that we knew. We just had to build this. Okay, so now we got to go to step number 2, which is get this only in terms of one variable. Now, I didn't give you any kind of a constraint, right? But there is one. What can you tell me about x and y? What restriction do we have on those? All right, so Bailey just said equals 200, right? So they add up to 200. X plus y is that total distance. So we do have a constraint. It's that x plus y is equal to 200. All right, so we can go ahead and solve for one and put them into the other. So I'm going to go ahead and solve it for y. So y is equal to 200 minus x. So we're going to get 200 minus x quantity squared plus 900 over 5. And now our formula is only in terms of x, which means we're good to go. All right, so there was step number 2. We now turn that equation into something that's only in terms of x. And this is where we do what we do. Right? Now we can differentiate, look at that derivative, figure out where is it undefined, where is it equal 0. use those critical points to tell us where she would actually have to enter into the water to minimize time to the drowning victim. Okay, I'm going to leave this one for you for practice. Now that this is all set up, I'm going to leave this for you to differentiate, find critical points, and so on. So on Wednesday, if after you take this home and you practice it and all that, if you want to see if your answer is correct, just remind me at the start of class, and I will tell you what the actual answer is. All right, so you can confirm it. But I want you to take I want you to try this one out on your own. Okay. I already did all the hard part. I helped you with the hard part. Now it's just a piece of cake. All right, so there's another optimization problem. It seems like it's very different, but it's exactly the same process as before. It's just, we had to use different kind of formula to build it. All right, so any questions on that one? How are we feeling about this? Just in general. I got a thumbs up. Oh, a couple thumbs up. Good. It's definitely one of those things that the more you practice it, the easier it's going to come. All right. So like I told you, this is probably one of the biggest uses of derivatives, actually, is optimization. This and linear approximation, by far, are the biggest things that we use derivatives for. So practice these, realize they are word problems, and word problems are how they are. Okay, so what I want to do with our remaining time, which is quite a bit still, we have another hour or so, I want to show you another way of dealing with limits that were difficult for us before. And these are going to be specifically limits of indeterminate forms. So let me remind you about those, because I showed you those before. So indeterminate forms, first of all, these were forms like 0 over 0. Remember when we did limits? The very first thing you would ever try to do is just plug the number in. But we ran into issues when it was 0 over 0, and we had to pull some sort of a trick. We factored, we rationalized, we did something like that. Well, 0 over 0 is what we call an indeterminate form, because it literally could be any number. So you've seen this one before. But there are some other indeterminate forms. Like 0 over 0, another indeterminate form is infinity over infinity. If you have an infinite number and you divide by another infinite number, you don't necessarily know what you get. You've seen this one as well. Look back just to last week when we were doing infinite limits as we were going to infinity. And when we had polynomials on top of each other, those were infinity over infinity. Sometimes it went to 0 if the bottom was bigger. Sometimes it went to infinity if the top was bigger. Sometimes it went to any number we wanted if the denominator and numerator were the same degree, right? So infinity over infinity was another one that, what is it? I don't know. Could be anything. Okay, well, so you've seen these, but here are a few more. Another indeterminate form is infinity minus infinity. What if when you plug in, you get infinity minus infinity? Well, maybe it's infinite, but maybe it's not. We don't really know. Another one is 0 to the 0. What do you get when you take 0 and raise it to the 0 power? Well, you might go, well, we should get 0, right? Because 0 to anything is 0. But then you go, well, maybe you get 1, because anything to the 0 power is 1. Well, it turns out it could be anything. 0 to the 0 literally could be any number. All right, so there's another indeterminate form. To go along with the powers, if you get infinity to the 0, actually, let me write that down here. I'm running out of space. We get infinity to the 0. That's also indeterminate form. No idea what it is. Here's another one. What if you have 0 times infinity? This is another one most people go, well, it should be 0 because 0 times anything is 0. But infinity is really big, and sometimes it's bigger than the 0. All right, so there's another one, 0 times infinity, right? And then the last one's another power. There's actually 7 different forms, and then the last one is 1 to infinity. So these are all what we call indeterminate forms. They literally can have any value, and we don't know just by looking at them what they are. All right, now you have, like I said, you've seen tricks to help you with the first two, 0 over 0 and infinity over infinity. We've run into those before. We haven't run into the other one. And so the question is, how do we actually determine the limits when we have these indeterminate forms? Well, this is where we're going to use this thing called L'Hopital's rule. So L'Hopital's rule okay, so it's spelled like this. So it's L with an apostrophe. And then it's HO with a little caret over the O. I don't know what that symbol is actually called in that case. It's French, and I never studied French, so I'm not sure. But that's over the O, and then it's Pital. Sometimes you'll see it written as hospital, Hospital, but it's L'Hopital's rule. So it's named after a guy who actually made a calculus book. One of the early calculus books was put together by this guy, L'Hopital. Just so you know, though, L'Hopital's rule was not proved by L'Hopital. It was actually proved by a guy by the name of Bernoulli. You may have heard of Bernoulli. A lot of people know that from physics. There's Bernoulli's theorem about how fluids flow. That's why like airplanes work. You get different pressures above and below the wings and blah, blah, blah. Okay, well, that's actually not the same Bernoulli. That's his brother. The Bernoullis, they were a family. There were the dad and 2 sons who were really powerful mathematicians and physicists at the time. This is the other Bernoulli. The mathematician Bernoulli, he did a lot of probability stuff. So if you've ever taken stats and you've seen, Bernoulli's distribution, yeah, that's that guy. But anyway, so Bernoulli was the one who actually proved it. L'Hopital just bought it. He basically paid Bernoulli for the rights to his theorem, put it in his calculus book, and then it became known as L'Hopital's rule. So that's probably the easiest way to get something named after yourself. Just throw out some money, right? Have somebody else do all the work for you. That's why there will never be an armbrust law, theorem, rule, because when someone comes around and says, hey, we'll give you money for it, I'll be the first to say, sure, no problem. I can buy me a lot of high quality root beer with that. Anyway, I digress. So L'Hopital's rule. Here's what L'Hopital's rule says. All right. So if we're taking a limit as x approaches a of f of x over g of x gives the indeterminate form zero over zero, then the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x. All right, so Eris, and I apologize, I didn't see this earlier. So Eris says, how can something times zero not equal zero? I'll explain. I'll explain when we get there. Basically, here's what's going on. These forms, remember that these forms are what you would get if you plugged in the point, but at a limit, we're not worrying about that point. We worry about what happens when we get close to that point. So just like with these, we're not really getting 0 over 0. We're getting 0 over 0 at the point, but not as we're getting close to that point. So it turns out that this actually is non-zero. Just like this is not actually infinity, but they're approaching 0 and infinity. And in that case, it cannot equal 0. I know it feels weird. And basically what I'm going to say is, like when we have something like, what's 0 divided by 0? It depends what kind of 0 we have. 0 times infinity? Well, it depends what kind of 0, what kind of infinity we have. It'll make sense when we look at it actually as a limit. But it's because we're doing a limit. We're not at that point, we're near that point. All right, so here's L'Hopital's rule. Basically, it just says, all you got to do, if you get 0 over 0 when you try to plug it in, you can immediately just take a derivative of the top and bottom and evaluate that limit. So this derivative on top and bottom is not the quotient rule. We're not differentiating the whole thing. We're differentiating the top and bottom separately. Okay, so let me show you why this works. I want to show you the proof real fast because it's kind of nifty. Let's actually just start with this limit as x goes to a of f of x over g of x. I can rewrite that as this. Now, you might go, wait a minute. You just subtracted something from the top and you subtracted something from the bottom. They're not the same thing. This is going to be changing the fraction. But I want you to notice f of a and g of a. Those are both equal to 0. Because, remember what I said here at the start? Is that this is the kind of thing that when I plug in a gives me 0 over 0. So f of a is 0 and g of a is 0. So what I really did right here is I just added 0 to the top and to the bottom. Or sorry, I subtracted 0 from the top and I subtracted 0 from the bottom, which means I didn't change anything. Okay, now what I'm going to do is I'm going to multiply top and bottom of this fraction by x minus a. So now I did build up my fraction. I multiplied in top and bottom by the same thing, 1 over x minus a. And that's not 0, because remember x is near a. So that's totally legit. And I think maybe you see what I'm doing. Look at the top now. This form right here should look familiar. If you go back to very late September, maybe early October, that's the definition of the derivative. So this is equal to f prime of a, and then the bottom is just g prime of a. And that itself is actually equal to the limit as x goes to a of f prime of x over g prime of x. So there's your proof of Logitel. It's actually pretty fast. And it's kind of nifty. But we started with this. We ran through some steps. And we ended up with the other side. So I don't know how much Bernoulli got paid for that, but he probably figured it was a good deal because it was an easy proof. The only consequence is his name was lost to it forever. Logitel got to get the credit. But Bernoulli's dead, doesn't care anymore now, right? When he was alive, at least he got some cash. Anyway, so there's Logitel's rule. This is why it works. So let me just show you how it's done, because it's pretty cool. You're going to really wish you knew Logitel's rule back in September, right? But in order to know Logitel's rule, we had to have derivatives. To know derivatives, we had to know how to do limits, which means we had to wait until we were ready for it. But let me show you how fast and easy this is. So for example, let's say we're taking the limit as x goes to 1 of 3x cubed minus 2x squared plus 4x minus 5. And we're going to divide that by 3x squared minus x minus 2. So you remember seeing things like this before. And so the first thing that we immediately try is to plug in 1. All right, so if we plug 1 into the top, we get 3 minus 2 plus 4 minus 5. Well, that's 0. You take 1, you plug it into the bottom, you get 3 minus 1 minus 2, which is 0. So this is that indeterminate form, 0 over 0. So what we would have done like 2 months ago, what would we have done back then? Like if you had seen this on an exam, what's your next step at this point? Before knowing Logitel's rule. Yeah, we'd have to use algebra. So Mariel just put in the chat box, we got to use algebra. We'd have to factor it, try to cancel factors, blah, blah, blah. Okay, no thank you. So instead, let's use Logitel's rule. Okay, just so you know, this is Bruce notation for I'm using Logitel's rule. I'm going to put over my equals, I'm going to put a little curvy L. That means I'm doing Logitel's rule. All right, so Logitel's rule says I'm going to get the same thing if I take a limit of the derivatives on top and bottom. Okay, so let's differentiate the top. I'm going to get 9x squared minus 4x plus 4. Okay, there's the derivative at the top. On the bottom, I'm going to get 6x minus 1. All right, so now let's plug in 1. Let's see what we get. So I plug in 1, I'm going to get 9 minus 4 plus 4, which is 9. On the bottom, I'm going to get 6 minus 1, which is 5. And that, my friends, is our answer. That's the limit as x goes to 1 of this function. Wow. Wow, no more algebra. No more rationalizing, no more any of that. We can jump straight to differentiate top and bottom, plug in, and see what we get. Let me show you another one. Now, this is one I know you know, because I told you you should know it. Of all the ones that we saw, this one you should just know. And that was this guy. Limit as x goes to 0 of sine x over x.
1.
So that's 1. Good. All right, so we already know that limit is 1. Let me show you how L'Hopital's rule confirms that. Right, we get 0 over 0, so let's differentiate. The derivative of sine is cosine. The derivative of x is 1. So that limit is equal to the cosine of 0, which is 1. Go back and look. Go back in your notes and look. Or maybe you can remember what we had to do to actually show this limit before.
It was a lot longer.
Oh, it was way longer. We actually used the squeeze theorem. We did some geometry. We built some like right triangles and compared it to areas of the sector of a circle and all that, right? It was a lot of work. L'Hopital's rule makes this a nothing, absolutely nothing kind of problem. All right, one more for good measure. And if you're not convinced after this third one, I'm not going to be able to convince you. But let's try this. Let's take the limit as x goes to, let's say, 3. And let's go with the square root of x plus 6 minus 3 over x minus 3. All right, so if you plug in 3, notice that we get 0 over 0. Right? Square root of 9 is 3. 3 minus 3 is 0. That's 0 over 0. Now, without L'Hopital's rule, we would have had to rationalize, get the conjugate, multiply top and bottom by the conjugate, distribute, factor, blah, 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 blah. Right? Watch how quick this is with L'Hopital's rule. So we're going to have the limit as x goes to 3. Now we need to differentiate. So on top, I'm going to get 1/2 times x plus 6 to the minus 1/2. The 3 goes away. On the bottom, I'm going to get 1. So this is the limit as x goes to 3 of 1 over 2 square roots of x plus 6. I plug in my 3, and I get 1/6. Go back, do this one the long way. Rationalize it. I promise you, you'll get 1/6. It's just going to take you like 5 times as long. All right, so are you convinced that L'Hopital's rule is something that we want? Are you wishing that you had had that a month and a half ago? Yep. All right. So, well, good things come to those who wait. But now we've got it. Now we've got L'Hopital's rule. All right. So for 0 over 0, we got L'Hopital's rule. Piece of cake. Okay, but what about all those other indeterminate forms, right? Because L'Hopital's rule is only good for 0 over 0. Except, check this out. What if we have infinity over infinity? Let's think about that one for a second. So we've got infinity over infinity. All right, so we're looking at limit, let's say x goes to a of f of x over g of x gives us infinity over infinity. Well, here's what I'm going to do. I'm going to rewrite this. So I'm not doing L'Hopital's rule. I'm not putting an L over here. I'm just doing algebra. This is the same as 1 over g divided by 1 over f. Just flip this bottom fraction over, turn it over and multiply, we get f over g. All right, so this top one was infinity over infinity. So what is this one now? What is 1 over infinity with a limit? What happens when we do 1 over infinity? All right, good, Bailey. It goes to 0. So 1 over g is 0, 1 over f is 0, and we're at the 0 over 0. Hey, wait a minute. That sure looks like the indeterminate form for L'Hopital's rule. And it is. So infinity over infinity actually is the same as 0 over 0. I know it doesn't feel like it, but it is. It does exactly the same thing. It's got exactly the same structure. So what that means is that for L'Hopital's rule, you actually do the exact same thing if it's infinity over infinity as if it's 0 over 0. You just differentiate top and bottom. Okay, so all this is showing you is that they're equivalent, infinity over infinity or 0 over 0. So for this guy, just do L'Hopital's rule. So I'm just going to put here, do L'Hopital's rule as is. You don't actually have to do anything differently if it's infinity over infinity. So let me show you an example. Let's look at the limit as x goes to infinity of 3x squared minus 4 over 6x squared plus 2x plus 1. All right, now you can actually just look at that one and tell me what the answer is, hopefully. What's that limit going to be as we go to infinity? So Suzanne just said 0. Remember your trick with these. Look at your degrees. So Bailey just said 1/2, which is seconded by Jessica. All right, it is going to be 1/2. Look at the powers. The degrees, they're both squares. So we take their leading coefficients. We get 3 over 6, which is 1/2. So we already know that it's going to equal 1/2. But let me show you that L'Hopital's rule will get us there as well. So we're going to do L'Hopital's rule. We're still going to take a limit as x goes to infinity. But now we're going to get derivatives. So we're going to get 6x on top, and on the bottom, I'm going to get 12x plus 2. So again, this was the infinity over infinity form. So now what happens if I plug in infinity? Well, I'm going to get infinity over infinity, which still doesn't help, but it's a form that I can use L'Hopital's rule on. So I'm going to do L'Hopital's rule one more time. The derivative on top is 6. The derivative on the bottom is 12, which gives us our 1/2. So it still got us the same place. I wouldn't use L'Hopital's rule here. I wouldn't. I would just use our little shortcut. But I did this for a couple of reasons. One, I wanted to show you that it works for infinity over infinity. But even more importantly, notice we had to do L'Hopital's rule twice. And sometimes you got to do that. Sometimes using L'Hopital's rule will get you another form that requires L'Hopital's rule. Well, do it again. Do it again. Do it again. Keep doing it until you no longer need L'Hopital's rule. So you no longer get an indeterminate form. All right, so 0 over 0, infinity over infinity, both of them, no big deal. Just differentiate top and bottom and take a limit of that. If that gives you 0 over 0 or infinity over infinity, do it again. Keep going until you no longer have indeterminate. All right, so those two are pretty quick. But there are still, if you remember that list, there were 7 total forms, so there's still 5 more forms. And the question is, can we use L'Hopital's rule? Can we apply L'Hopital's rule to those? And the answer is most definitely. Let me show you. All right. Actually, before I do that, any questions so far? Are we doing okay? All right, so here's your next form. What if we have 0 times infinity? All right, so this is going to be the limit as x goes to a of f of x times g of x. And one of those is 0, and the other one is infinite. Okay, so let me show you an example. What we're talking about would be something like the limit as x goes to infinity of 1 over x times e to the x. Actually, no, I don't want that one. Sorry. Let's do x times e to the minus x. So again, notice what that gives us. That's infinity times 0. E to the minus infinity, that trends towards 0. All right, so this is definitely not 0 over 0. It's also not infinity over infinity. Well, here's what we're going to do. So this is not L'Hopital's rule. Again, this is just, I'm doing algebra. What if instead I think of this as f of x over 1 over g of x? So it's kind of the same trick I did with the infinities before. Remember, I turned the infinities into zeros by doing 1 over. Well, that's what I'm going to do here. F times g is the same as f divided by 1 over g. And now what this is going to turn into is 0 over 0. Because 1 over infinity is 0. So by doing this little trick, it turns it into a L'Hopital's rule form. So all you got to do is take one of the functions, take its reciprocal, and put it in the denominator. All right, so let's do that with this guy. So again, I'm not doing L'Hopital's rule yet. I'm going to rewrite this as x over 1 over e to the minus x. So I'm just making it 1 over that guy that goes to, or the e to the minus x. So now if you look at this, that's the same as x over e to the x. So algebraically, this is the same as what we started with. But now check it out. What happens if you put in infinity? Well, you get infinity over infinity, which means we can use L'Hopital's rule. So I know that when I wrote it over here, I made it 0 over 0. It is possible that it turns it into infinity over infinity. But either way, that's just as good of a form. So let's do L'Hopital's rule. So we're going to take the limit as x goes to infinity, and I have to differentiate top and bottom. So the derivative of x is 1. The derivative of e to the x is e to the x. So that gives me 1 over infinity. So what is that limit? Yeah, that one's 0. So this is one whose limit is 0. All right, so this is a case where 0 times infinity ended up equaling 0. All right. And you may remember Ayers asked earlier, he's like, well, how can you ever get something that's not 0? Let me show you an example of one that isn't 0. So let's do the limit as x goes to infinity of, let's do, hold on a second. Now let's do this. Limit as x goes to 0 of x times natural log of x. No, that's not going to do what I want. I'm trying to make up one in my head that will do what I want, and I'm running it. Okay, here. Limit as x goes to infinity of 1 over x times e to the x. So if we plug in infinity, this is going to give us 0 times infinity. All right, so let's change it algebraically. I'm going to make this e to the x over 1 over x. Yeah, so I didn't want to do this one, but it's going to do what I needed to do. All right, so one more step before we do L'Hopital's rule. Let's just clean that up a little bit. That's the same as e to the x over x. because the reciprocal of 1 over x is x. All right, now if we go to infinity, this gives us infinity over infinity. So we're ready for L'Hopital's rule. All right, so L'Hopital's rule then says this is the limit as x goes to infinity of e to the x over 1. The derivative of e to the x is e to the x. The derivative of x is 1. And this guy is infinity. So this time, 0 times infinity gave me infinity. Okay, and that's what I mean when I say it depends what kind of 0, what kind of infinity. It really matters how these things are approaching 0 and infinity. Infinity is a weird thing. If you're looking at this and you're just going, yeah, none of this makes sense, doesn't seem like it should work this way, that's okay. Human brain does not understand infinity. We're not built to understand infinity. Everything we experience in life is finite. So this like going on forever stuff doesn't work for us. Well, but if we trust the math, and you can trust the math, it's definitely, everything is legit. It turns out that, yeah, in this case, sometimes 0 times infinity doesn't equal 0. Because it depends on what kind of zeros we got, what kind of infinity is happening. And when I say what kind, it's basically how are those functions approaching 0 and infinity. All right, well, that's the trick for 0 times infinity. You just turn it into infinity over infinity or 0 over 0 by dividing, because multiplying is dividing. Dividing is multiplying. It's just the reciprocal. All right, so that took care of that one. So we've got 3 down. 0 over 0, infinity over infinity, and 0 times infinity. Right, we've got those 3. Well, we still have 4 more to do, but we're going to take care of 3 of them all at once. We're going to take care of all those ones with exponents. Okay, so here were those 3 forms. We had 0 to the 0. We had 1 to the infinity. And the other one I'm missing is infinity to 0. I have to think about that for a second. All right, so the question is, how do we deal with those guys? Well, let's think about it. First of all, if we want to use L'Hopital's rule, we want either 0 over 0 or infinity over infinity. So we need to have some sort of a division. Multiplication would be just as fine. But basically, we need either multiplication or division instead of exponents. All right, I think some of you are savvy enough to start seeing this. What can we do to make it so that we don't have exponents anymore, but instead have, say, multiplication? Where have you seen that done before? Bringing powers out front. Yeah, thanks, Bailey. This is just begging for natural logs, right? Because check this out. What if we have y equals 0 to the 0? And I take a natural log of both sides. What I'm going to have now is the natural log of y is equal to 0 times the natural log of 0. And the natural log of 0 is infinite. So by taking a natural log with the 0 to the 0 form, we get 0 times infinity. 0 times infinity is another indeterminate form, but it's this indeterminate form, which means we just need to do one more step to make it a division, and then we can use L'Hopital's rule. Similarly, if we had done y equals 1 to infinity, done the same thing, we would have natural log of y is equal to infinity times the natural log of 1. Well, the natural log of 1 is 0. So the same thing is happening there. If we do infinity to the 0, we're going to get the natural log of y is equal to 0 times the natural log of infinity, which again is 0 times infinity. So for all of those forms, what we're going to want to do is take a natural log, because then we can do L'Hopital's rule. But what we're going to have to remember is that we took a natural log, so that when we actually calculate this limit, we're finding the limit of the natural log of y, which means we have to convert back using exponents to get back to our original y. So let me show you how that works with a fairly easy one. So let's start with this guy. Let's do a limit as x goes to 0 of x to the x. So clearly, you can see that this gives us 0 to the 0, which is one of those indeterminate forms. So instead of x to the x, right, instead of looking at y equals x to the x, let's take a natural log. So the natural log of y is going to equal x times the natural log of x. And now if we do a limit, notice that what this gives us is 0 times infinity, which is now an indeterminate form. So let's investigate this one. Let's calculate this limit and see what we can get. So since we have 0 times infinity, we need to turn it into a division problem. So I'm going to make this the limit as x goes to 0 of the natural log of x divided by 1 over x. I have to make one of them, I have to take the reciprocal of one of them. I figure it's easier to take the reciprocal of x than natural log of x. That's why I did it this way. You could have done it the other way if you wanted. I just think this is going to be easier. All right, now if you look at this, this is going to give us infinity over infinity, which means we're ready for L'Hopital's rule. All right, so let's do L'Hopital's rule. So I need derivatives. The derivative of natural log is 1 over x. The derivative of 1 over x is minus 1 over x squared. All right, so now the question is, what happens when we plug in 0 here? Well, before we do that, let's simplify, but there was just a question. So wouldn't 1 over x be 0? Not if we're going to 0. If we were going to infinity, it would be 0, but we're going to 0. So you take 1 and you divide it by something really, really, really tiny, you get something huge. Yeah, so we got to be careful. We got to watch for where we're actually approaching in terms of what it's going to do. All right, well, let's just do some real quick algebra on this. 1 over x divided by 1 over x squared. That's the same as 1 over x times x squared over 1. Let me put the minus sign on here. Right, dividing by a fraction. And one of those x's cancels, so we're left with the limit as x goes to 0 of negative x. So that thing simplified down pretty easily just to negative x. But this one now we can take its limit. So what's the limit as x goes to 0 of this? Well, it's 0. But don't put a box around it. If you enter this into your homework program, into the computer, it's going to give you the red X. And then you're going to send me the message and say, how come I got the red X? And I'm going to say, because you forgot to remember something. What did I tell you that we had to remember when we were doing this?
The limit?
Not the limit. What did we do at the very beginning? Yeah, thanks, Alia. We have to remember that we took the natural log. So this guy is 0, right? I mean, this number 0 matters. This is important. But that number 0 is what the natural log of y goes to. So remember, the limit we are looking at was this guy right here. The limit is x goes to 0 of x log x. That's the thing whose limit is 0. But the x log x is actually just the natural log of y. So what we know is that the natural log of y is actually going to 0. Which means we need to get y. Well, we're going to do that by just converting it to exponential form. So y is equal to e to the 0, which is 1. So it turns out in this case that 0 to the 0 gave us 1. So the limit is x goes to 0 of x to the x is equal to 1.
So do we have to type out the whole thing when we enter it, or do we just have to type out the 1?
It depends what they ask.
Okay.
How sometimes they have stuff outside the box. They'll be like, oh, look, we already gave you the pi. Now you plug in the other number or whatever. So it really just depends. But if all it says is, what is the limit of, x goes to 0 of x to the x equals, yeah, it's just 1. That's the number that this function approaches as we get closer to 0. It gets closer and closer to 1. But to find it, we had to do a bunch of algebra along the way, which is very little bit of calculus. Again, let me just remind you how much of this was calculus. The calculus was right there. That's it. That's the only piece of this entire problem that was calculus. Right. But yeah, so the answer to this would be 1. This limit equals 1. So when you're in one of these 3 forms that have the exponents, take a log, because that's going to turn it into 0 times infinity, which then will let you turn it into either 0 over 0 or infinity over infinity, so that you can use Logitel's rule. But then you have to remember, you got to make sure that you remember that you took that log so that you can go backwards, right? So like if this number had been 1, let's say, then our actual answer would have been e to the first. If this number had been -4, our actual answer would have been e to the -4. So on and so forth. Okay, so you always got to make sure that you turn it back into y. You have to undo that log.
Hey, Bruce.
Hey, what?
Can you just remind me how you got from from the limit as x goes to 0 of x times natural log of x equals 0 times infinity to the next step?
Okay, from here to here. Sure. So when we have, just let me go back to it in general. If we've got f times g, you can actually write this as g divided by 1 over f, or you can write it as f over 1 divided by g. And this just comes from how division of fractions works. When you divide by a fraction, it's the same as multiplying by the reciprocal. So like this first one would be the same as g of x times f of x over 1. Because I just flipped it over and multiplied. This one would be the same as f of x times g of x over 1. Because again, I just flipped it over and multiplied. So what I'm doing is I'm actually doing that backwards. I'm starting with this multiplied form and turning it into a division. And so that's what I did here. I took that first x and I turned it into division by 1 over x. Okay, right there. That clear that up a little bit, Alia?
Yeah, thank you.
Yeah. I'm not really convinced by that, yeah, but
I'm not either.
maybe you and I can chat about it later sometime after you have time to ruminate on it.
Yeah, no, I think I understand that step. This whole process is just confusing to me.
There's tons of algebra here, right? Like there's an absolute ton of algebra that we're using to manipulate stuff to turn it into form where we can use the calculus. So we're definitely pulling out all kinds of tricks that seem wrong, right? Like if I said, what's 2 times 5? You never think of it as, oh, it's 5 divided by a half, right? You never do that. But it's the same thing. 5 divided by a half is the same as 5 times 2. So we're not used to doing that. We're just used to doing multiplication. You don't turn multiplication into division, ever. We only ever do it the other way around, right? We turn division into multiplying all the time. We don't like going the other direction. And that's what we're doing now. We're taking multiplying and we're turning it into division. And since it's something we never do, it's very uncomfortable. Because we never do it. But we're basically just going backwards of what we always do, though. So it's okay that you feel a little bit weird about it. You should. But you should also trust that it's okay because we're just doing the same thing we do all the time backwards.
So for all of these other forms, are we always trying to get them into either 0 over 0 or infinity over infinity first?
Yep, 100%. Because if it's not 0 over 0 or infinity over infinity, we can't use L'Hopital's rule. L'Hopital's rule only applies if it's 0 over 0 or infinity over infinity. So that is the ultimate goal. You want it in one of those first 2 indeterminate forms. All right, so other questions at this point? Because we still have one more form I want to show you, infinity minus infinity. Because the question is, what do you do with something like that? All right, so let me show you an example, and we'll kind of talk through what the process is when you're there. All right, so here's our last one. What about infinity minus infinity? Now, the first two, 0 over 0, infinity over infinity, really easy. What do? L'Hopital's rule. 0 times infinity, what do? Turn it into division, then L'Hopital's rule. For the 3 with the exponents, right? 0, 0, 1 to the infinity, infinity to the 0. You take a natural log, then do a division, turn it into division, and then do L'Hopital's rule. So very systematic. For infinity minus infinity, this is one where you kind of have to just wing it a bit, right? In terms of what steps you're going to actually do. But the goal is going to be, just like always, turn it into 0 over 0 or infinity over infinity. So it's actually really easy for me just to say that, right? That's all you got to do. The process itself might be a little bit more difficult. However, we can eventually get there. All right, so let me show you. Let me show you what I mean with an example. Let's try this guy. Let's do the limit as x approaches pi over 2, and I'm going to put a minus on that. So we're going to be approaching pi over 2 from the left of tangent of x minus secant of x. So I made it a one-sided limit. I don't know if you remember tangent and secant, but their graphs at pi over 2 have an asymptote, and on either side, they're going to a different direction, plus infinity versus minus infinity. So I need to make it a one-sided limit for it to be good. It turns out with L'Hopital's rule, it doesn't matter, one-sided, two-sided, as long as we have infinity over infinity or 0 over 0, we're good. All right, now both tangent and secant are infinite here. So this is infinity minus infinity. And so your first inclination is probably just to say, well, then this must equal 0. Because infinity minus infinity equals 0. But the problem is that's not always the case. Because if one of them grows faster than the other, then it can still blow up. If they grow at almost the same rate, this actually can be a finite number other than 0, right? So it's just one of those things we don't really know. All right, so somehow we have to turn it into division. Well, in this case, here's what I'm going to do. I'm going to use trig. Let's first turn those into sines and cosines. So tangent is sine of x over cosine of x. Secant is 1 over cosine of x. So I can actually combine those two together into sine x minus 1 over cosine of x. So I haven't done a spot of calculus yet, right? No calculus. This is just trig manipulation. But look at this form now. The sine of pi over 2 is 1. So 1 minus 1 is 0. The cosine of pi over 2 is 0. So this form is now 0 over 0. So we started with infinity minus infinity. Using a little bit of trig brought us to 0 over 0. But now we're ready. Now we're ready for L'Hopital's rule. All right, so let's do L'Hopital's rule. We're going to differentiate top and bottom and evaluate it at pi over 2. So by L'Hopital's rule, we're going to get the limit as x goes to pi over 2 from the left of, well, on top, we're going to get cosine of x. On the bottom, we're going to get minus sine of x.
Isn't that negative cotangent?
It is negative cotangent. Yep. But let's actually evaluate it here, because I think it'll be easier for us. I think most people know better the values of sine and cosine of pi over 2 than cotangent. So let's think about pi over 2. Cosine of pi over 2, that's a 0. The sine of pi over 2 is 1. So this time we get 0 over minus 1. And we're actually done. We can do this division. We don't have to do L'Hopital's rule again. 0 divided by minus 1 is actually just 0. All right, so in this case, we do end up getting 0. Basically, what this tells you is that tangent and secant both grow at exactly the same rate. So this thing equals 0. So the trick with infinity or minus infinity is to somehow turn it into infinity over infinity, and that's going to vary. It's going to really depend on what the structure is. But this is a pretty easy example to see where if we use a little bit of trig, we can get there. All right. Anyway, so this is L'Hopital's rule. Just take it for what it is. It's a super, super easy way to evaluate limits that give you 0 over 0 or infinity over infinity. Those aren't the ones that are going to be tough. Those are easy. You just differentiate top and bottom, plug in and go. The ones that are going to be tricky are the ones that require us to do algebra to get us into one of those two forms. So make sure you practice your logs, practice the turning multiply into divide, because those are steps that you're going to have to do for these other forms. All right, so there you go. There's L'Hopital's rule. All right, so a couple of things for you. First of all, there's homework due tonight. Don't forget to get in there and finish those out. We do have an exam that's going to be coming up on Friday. So our next exam is this coming Friday. What it's going to cover, because I know everybody's dying to know, it's going to pick up where the last exam left off. All right, so if I recall correctly, we just went through the end of the chapter, right? Let me just grab my book here real quick. Yeah, so the exam, the last exam went through the end of chapter 3. So this exam on Friday is basically going to be on chapter 4. So starting at 4.1, and it's going to go through the applied optimization. So not L'Hopital's rule, not what we did today. We'll save that for the final, but only through optimization. So that's 4.7. Okay, so just to remind everybody here, we have an exam on Friday. And it's on 4.1 through 4.7. We will talk more Wednesday, next class. We'll spend some time reviewing and talking about what it's going to cover and what it's going to look like. All right, so don't worry, we'll do that on Wednesday, but just so you can start 4.1 through 4.7. All right, so it's all applications of the derivative. That's all this chapter is anyway. All right, so that's going to happen on Friday. We'll spend some time reviewing on Wednesday, talking about stuff like that. And then next week, no class. And then one more week of class and we're good to go, okay? So get your homeworks done for tonight and get ready for that exam on Friday. All right, so anything else before we pause this recording and call it a day? Any other questions? Alia, is there no class at all next week? Correct. No class at all next week. So the entirety of Thanksgiving week, we are off. All right. Okay, well, with that, you guys have an awesome couple of days, and I'll see everybody on Wednesday.